So our next goal, now that we know how to graph sine and cosine in all their glory, is to learn how to graph the other four functions. Right? Tangent, cotangent, secant, cosecant. The way we're going to break this up, so this is 6,5 and then 6,6 again. 6,5 talks again, everything doesn't have a phase shift in 6,5. It doesn't have that extra horizontal shift. And then 6,6 throws in that phase shift. Right? But the way we're going to break this up in 6,5 is we're going to learn how to graph tangent. I'll just get to start today. And then we're going to learn, in general, how to graph a reciprocal function. Because if you remember, those three functions I put there, cotangent, secant, cosecant, those are all reciprocals of something else. Cotangent of x, what's cotangent the reciprocal of? Tangent is 1 over tangent. What about secant? What's secant the reciprocal of? It's 1 over cosine. Right, so secant is the reciprocal of cosine. And then cosecant, 1 over sine. So first we'll graph tangent, which is its own new thing, but then we're going to learn a method that helps us graph, just in general, a reciprocal function, and we'll apply that method to all three of these. Okay, so we can kind of group these together and do them in one fell swoop. But this guy we have to treat separately. So the graph of y equals tan x. Now for sine and cosine I plotted points. I guess I could plot points for tangent, but most likely, because it has asymptotes, the points you get are not going to be connected and it's just going to look ugly. So instead of going about this by plotting points, I'm going to take a more analytical view and just try to break down what tangent is, okay, and how it behaves. So there's four important things you really need to grasp in order to get an easy, good-looking picture of tangent. So the first one, and through all of this, you want to be thinking that tan x is equal to sine x over cos x. And again, x is an angle, and y is your ratio on the unit circle. So the first important fact I need to know to get a decent graph of tangent is that the period is pi. You guys remember that? Tangent repeats every pi, not every 2 pi. Right? Since tangent is y over x, if you remember the way this works, whether you do theta over here and calculate y over x, or you do theta over here, pi later, which is negative x, negative y in the unit circle. In both of these cases, tangent's the same, right? Because the negatives will cancel when you do y over x. So tangent repeats every pi. That's the first important fact. Next. The graph of tangent has vertical asymptotes at odd multiples of pi over 2. How do you, if you remember, how do you find vertical asymptotes? Any idea? Any recollection?
Look at
the slant asymptotes.
Set the denominator go to 0.
Set the denominator to 0. That's vertical asymptotes. So to understand the vertical asymptotes of tangent, we have to take this denominator and set it equal to 0. So I'm going to have to solve, I'm going to have to figure out where cosine of x is equal to 0. So coming back to a handy-dandy picture of my unit circle, where's the x value on my unit circle going to be 0? Up here, right? That's where cosine 0, or down here. So what angles are those at?
Pi over 2.
Pi over 2? Or 3 pi over 2? Is that all? No, you can keep going. Right? You can do 5 pi over 2, 7 pi over 2, 9 pi over 2. You can go the other way, negative pi over 2. Right? There's a bunch of different names for these two axes. Right? You can go this way, negative pi over 2, negative 3 pi over 2. So I said, up there, the graph of y equals tan x has vertical asymptotes at odd multiples of pi over 2. So what that means is 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, any odd number over 2, any odd number pi over 2, tangent's going to have an asymptote. So this guy, the solution to this is x equals x is in the set. Negative 5 pi over 2. Negative 3 pi over 2. Negative pi over 2. Pi over 2. 3 pi over 2. 5 pi over 2. You just keep going. The same pattern. Now, because we're only graphing one period, we're only going to focus on these two. Because they're the easiest ones, they're the smallest ones. Right, between negative pi over 2 and pi over 2, negative pi over 2 and pi over 2 is one period of tangent. There's a whole pi between them. But don't forget about these. These are going to come back. Right? These are not the only two asymptotes for tangent. They're just the only ones we graph, because we only graph one period. The next fact there, the graph of tan x has a 0 at each integer multiple of pi. What's a 0? What's that mean, has a 0? What's a 0 of a function? You don't remember? X-intercepts. Zeros of a function are where the function equals 0, which are the same thing as x-intercepts. So tangent has zeros or x-intercepts when the whole thing is equal to 0. But in order for this whole fraction to be equal to 0, you have to make sine the top equal to 0. Right, the bottom gives you asymptotes, the top gives you x-intercepts. Right, the only way a fraction can be 0 is if the top is 0. So to get the zeros, you have to solve this equation. Where's sine equal to 0? That's where your y values are 0 on the unit circle. Here and here. 1, 0, and negative 1, 0. But I need angles. What's the angle here? 2 pi or 0. What's the angle over here? Pi or 3 pi if you keep going. Right? 0, 1 pi, 2 pi, 3 pi, 4 pi. Or you could go backward, negative pi, negative 2 pi. So that's why I put up here the graph of tan x has a 0 at each integer multiple of pi. This means whole number multiples of pi. 1 pi, 2 pi, 3 pi, 0 pi. So for this guy, you have these kind of x-intercepts. Negative 3 pi, negative 2 pi, negative pi, 0, pi, 2 pi, etc. And then the last thing I told you, you're going to wonder why I told you this. Maybe I'll show you in a second. Maybe I'll justify it. Maybe I'll let you think about it. The last thing I told you were 2 extra points. And this is kind of the reasoning for this is to help you figure out how you approach the asymptotes, to help you figure out whether the graph is going up or down. I told you that tangent of pi over 4 is 1. Do you believe this? Why? Because it's there. Because it's written in black and white. Anything written in black and white, you believe.
Because in special triangles.
Yeah, it's your special triangle. Pi over 4 is a special angle. Right? On the unit circle, if you remember it on the unit circle, it's where you have root 2 over 2, root 2 over 2. So if you do tangent, you get 1. Because tangent is y over x. So tangent of pi over 4 is 1. What about tangent of negative pi over 4? Negative 1 because you're down here. Right? Negative pi over 4 has a negative y value. Right? Fourth quadrant, you can have a negative y value. So what that means are I have 2 points on my graph. When x is pi over 4, my y value is 1. That's what this first fact means. When I plug in pi over 4, I get out 1. So this is a point on my graph. The second function, the second statement says if I plug in negative pi over 4, I get out. So with these 4 facts, I can get a decent graph of tangent. So let me toss it up here. So the graph of tangent. The graph of tangent has vertical asymptotes at odd multiples of pi over 2. So let me put those on there. Pi over 2, 3 pi over 2, etc. Negative pi over 2, negative 3 pi over 2. Vertical asymptotes, so I'll put in lines. Then I know that it has zeros at integer multiples of pi. So I have an x-intercept here because that's 0. I have an x-intercept at pi because pi is right between these two. I have an x-intercept at negative pi because negative pi is right between these two. So the way tangent breaks down, it has an x-intercept right in the middle of its 2 asymptotes. The other piece of information is that when I'm at pi over 4, my y value is 1. Pi over 4 is here. Because it's halfway between 0 and pi over 2, 1 is up here. When I'm at negative pi over 4, I'm at negative 1. So here's negative pi over 4. I'll be down at negative 1. So tangent has to go through all of those points and approach the asymptotes. Usually, I would probably draw it in 2 pieces, just to make so it doesn't. I mean, it's not a straight line; it's got curve to it. Like a snake, but it's squished between 2 asymptotes. And because the period is pi, it's going to repeat over here the same exact shape. So this is y equals 10.